Yeah, my name is Jerin and I work for Marvell. And this presentation is regarding the DPDK Trace library and the usage of this and the implementation details. So as an agenda, let's get started with why we need tracing and what is tracing. And we'll be explaining DPDK Trace library features. And in terms of usage, we'll be telling how to add a trace point and how to control the trace points and what are the different tracing modes. And as a quick start, like the commands to try tracing with upstream DPDK. And I have attached some of the trace viewer screenshots so we can see how we can view the trace which is emitted by DPDK. And that's the usage part, and we'll move with the implementation details where we are using a common trace format, open source trace format. So we'll be giving an overview of that, what the format it's all about. And so we'll be getting into next level of details like so each trace file has metadata objects. I will give more examples there, but we'll see a meta file. It's specifically crafted for DPDK to get a higher performance. And last not but least, the trace buffer memory layout, how trace buffer memory layout is organized to have a better performance and without CPU locking, or how we can get a better performance with this. That's pretty much agenda, and let's get started with the points. So the first thing is like why we need tracing. So it so happens that so we have DPDK providers like Marvell who gave the DPDK libraries to the customers. So typically it happens that like we will not have access to the customer application, and all of their use cases cannot be tested with standard applications like TestPMD or L3 forward. So there are quite a lot of situations where like there are specific problems that comes in customer applications, and obviously it's a proprietary code and they don't want to share the code. So the middle ground is like once we enable the trace points, and once we get the trace file, once we open through the trace viewers, then you can see what are the API sequence it's happened and what are the request and response associated with that. So that way we can get to know the personality of the application, and we can start suggesting, or we can get more insight like what they're trying to do and how to help them without sharing their proprietary applications. That's the main use case. The second use case is like we have an RT log, which is a printf, or meaning text-based debug, meaning logging system. The downside is like we cannot use a printf for debugging time-sensitive fast path issues, where once we add the printfs, then the complete behavior is going to change and the performance is going to dip, and you will not see the same problem again. So trace is going to help in that places where without having a much overhead, how we can debug a system. So in terms of overhead, it's like one cycle for instrumentation overhead, where if you insert a trace point and if you just disable it, so it's just a one cycle overhead. And if you enable it like on ARM64 and x86, it's like 16 to 17 cycles to emit a trace, where if you use some of the other tools like LNTNG and other things, it's like 120 to 130 cycles to emit a trace point. So it's like highly performance optimized thing, specifically crafted for DPDK requirements. And so another thing is like RTLog, it's using a text format, and this is going to use a binary format to reduce the log size and amount of data we can capture in a given period of time, right? So that's using a binary format. And it's supporting a multi-core tracing without locking. So I will get into the specifics of how we can able to do that. So yeah, so that's one part. So we don't need to have a lock. So it's extremely fast, even if it in multi-CPU scenarios. It's not, yeah, another point is like, it's not really why we need tracing, but as a requirement. So we need to, yeah, we were evaluating what would be the trace format. So we finally latched on an open source trace format so that we can reuse the standard trace viewers. So you don't need to rewrite you don't need to write the trace viewer applications. All you need to do is create the trace, and we can view with standard viewers. And also, if you use standard open source formats, then you can reuse the post-trace analysis tools like how much time CPU is idle. And so if you run through the trace points or trace buffers, then if you start accounting each trace points, then you can have a lot of post-analysis tools like if, let's say, for example, like if you emit a trace on each RX burst, so then you can see like what's the time gap between two different RX bursts happen. So you can have a lot of post-trace analysis tools in Python or any other language where you don't need to have, it's easily you can get integrated those kind of tools. So yeah, so now let's get to the basics where what is tracing, right? So tracing is a technique used to understand what's going on a running software system. So you can assume it's like a tape recorder, and we will be recording the events, and once events are recorded, there are different modes. I will get into that, how we can record. But once events are recorded, then you can use a trace viewer to visualize the different, meaning how the system events been generated, and the time gap between each events and such, right? So that's the overall definition of tracing. And it's quite added, it's added as a trace library feature in DPDK. It's added in 20.05, around 2 years back. And we've been we are modifying each subsystem, or we are adding each subsystem with trace points, so that it has an inbuilt trace points for each APIs, so that others people does not need to add, meaning the customers does not need to add new trace points for this thing. So we just keep adding different trace point on almost all the APIs. We keep adding it. In this release, we have submitted a patch for adding trace points to all the ETH-Dev APIs. So we have done the basic APIs, but we keep extending that to have a complete coverage of all the APIs. Yeah, so the next thing is like you can save the trace buffer, the buffer which contains the trace, to the file system at any point of time. And we have two modes, overwrite and discard. I will get into that in a later slide. And we have a string-based trace object lookup. Yeah, I will get into that more details. Then we have a means to enable and disable the trace points based on a regular expression. And we are using a standard open source trace format called CTF. It's compatible with LLTNG in terms of viewing the trace. And the definition of, meaning the specification of CTF is here. So anyone can take a look at it. So now the next point is like how we can add the tracing, right? So it's quite simple. So all you need, in order to create a trace point, first, there are two operations. One, we need to create the trace point that we'll outline here. So the first point is you need to create a header file and call the trace point macro. And the first parameter is the function. It's going to be called by the application. And the trace point arguments. So it's like So if you see this function, its macro is going to get expanded like this. So where app trace is a function is going to come as a function on all these things information will be added by the macro. And second parameter is the function arguments. And third parameter in this case, third parameter is a emit string. So basically, whatever you pass, it's going to emit, right? And we also give the data type for all the cases where, like, how do you want to emit U64, I64, 32, 64, 16, U8, I8, long, size C underscore T, float, and other thing. So basically, creating a trace point is like, you define the function and you define the arguments, what are the inputs it's going to take, and pick the data types from this thing and just keep adding to this thing so that you can craft a trace point based on your need. So basically, this macro, when it gets to expanded, it's going to come something like this, where, yeah, it's a function name, and trace subsystem has some prologue and epilogue. So those things will be emitted in the code. And all you care about, like function name, what to pass, and whatever you passed, how to use the specific data type functions to emit that. So that's the one header file. So you tell how to add a trace point, and just you need to register that trace point. So you give a header file of the trace point, and just give the function what you given earlier, and just give a name to this. So the name is required so that we can use regex and globing actions where you can enable or disable this trace point later, right? And in DPDK, we are following a convention like the library trace points, we have like lib.ethdev. The specific trace point, right? So that useful is like, since it supports regex, like if you want to enable all the ethdev trace points, you can say lib.ethdev.star, right? So all the ethdev will be enabled. So we have a namespace. In this specific example, it's not in library, so it's just an application tracing. So just give a namespace called app.trace. But library, you can give any name, but we are following a convention in a DPDK to add a trace points inside the library by giving lib.library_name.the trace point, so that it's easy to further control that using a string operations. Yeah, so now let's get to how to control the trace points, right? So the first thing is like the name what you give, you get a trace point object back, and with that you can enable a trace point and disable it. It is all can do it in runtime, and you can check is it enabled. And this is where like you can control a set of trace points where giving a regex pattern. Like the string is like if it is a lib.ethdev.star, all the ethdev trace points will be enabled in one shot, right? So that's a typical use case. So we given both f and match, like globing kind of a pattern, meaning APIs, and regex more, meaning you can give star, asterisk, kind of a very complicated regex pattern also we can give. So that's the high level APA on the controlling the trace point. And I would like to touch base on other aspects, like on adding a trace point, it's like, even though instrumentation cycle is like one cycle overhead, we decide to have a build option so that we don't need to unnecessary waste cycles in fast path. So by default, so first point is like, instead of using trace underscore point macro, you just need to use trace point underscore FP. FP denote for fast path. So that's the one you need to use for fast path. And by default, it's disabled or compiled out. And you can use a Mason option, enable trace FP, to enable this kind of fast path traces, so that we kind of adding zero overhead to the DPDK library whoever does not want to use trace. Okay, now there are two different trace modes. The first one is called overwrite. So in this case, like when trace buffer is full, and it just overwrites the previous captured events, and it just keep on updating the content. It just keeps overwriting the buffer. Another thing is like when trace buffer is full, then new trace events will be discarded and it's no more recording the thing. So yeah, this can be controlled by two ways. There is exclusive API for that to set the mode. So it's for runtime. And there is an EAL option to control the trace mode on the application mode tab. So you can specify overwrite and discard. By default, it's overwrite. And this is on where the trace files are located, right? So there are two means to save the trace buffers to the file system. So one is like exclusively you can call RT trace save. So upon calling this API or upon calling RTEL cleanup, the trace buffers will be saved to the file system. And where the files were stored, by default it stores in the home directory with the DPDK Traces directory. And this is like DPDK application name and the time in which it's got created. And you can override this path by giving a trace dir as an EL argument. Okay, now other aspect is setting a trace buffer size. So yeah, you can giving an EL argument where you can specify the trace buffer size in either in bytes, in kilobytes or megabytes. So per core, there will be so much of buffers will be created per core. And by default, the buffer size is 1 MB. You can override to the thing what you want. Now let's get into the quick start, like how we can try trace without top of tree DPDK build, right? So the DPDK test is a standard application. So we can, this is like simply starting this application and doing a quit just to exit the application, right? So this is, yes, because by default, inbuilt, we added a lot of trace points, so you can see traces with that. So this is just executing a standard application. You don't want to do anything specific. I just given a no huge page so that you don't have any dependency, but if huge pages are given, then the trace buffers are created in huge page. Otherwise, it will be in heap memory. But trace, it's going to support with both modes. I just given a one core to reduce the number of trace points. And this is the important part where this is where the pattern you are going to give. In this case, like I'm telling, like emit all the trace points, but you can give more fine-grained subsections like lib.ethdev or lib.eventdev, lib.cryptodev, or lib.stars or the library things you can give here. So this currently, meaning if you just give .star means all the trace points. Yeah, so what it matters is like, yeah, so if you give this trace, once trace is enabled once you give this thing trace is enabled, then you can see a print where the trace points were, the trace buffer stored in a file system. So yeah, so this is like DPDK file name, DPDK application name followed by the time where it's got created. So that's pretty much it. Using standard applications, you can create the trace. There's nothing specific to do. All it's upstreamed. And now it comes to just trying to give a screenshot of a couple of standard trace viewers. So this one is the Babel trace. It's the command line based trace viewer interface. It's an open source. It's used in LNT-NJ also. It's the same. Since we are using CTF, then we can reuse all these tools as is. So basically, yeah. So we just give the path, the one I previously showed where the trace points where trace buffers are stored. Just give that path and Babel trace. So yeah. So now we can see that. So it will spit out the time stamp and the delta between each events, and it's going to spit out the trace name. So it's like we have inbuilt one for memory like lib.el.mem. All the malloc, zmalloc, lookup, memzone, and other things already added the trace. And it's going to say which CPUs initiated this thing, and the name of that thread. In this case, it's a DPDK test because the DPDK test setting as a name. And the next part is the arguments to that thing, right? So which we see in area like how to add trace point, right? So if you want to map to this, if you want to map to this thing, like in this specific case for malloc, it's like we'll be emitting a trace point with like a type as a string, size underscore t as an object, and I think uint 16 socket, an integer, and the pointer, right? So we'll be just emitting that. And yeah, so in fastpath, we'll have a limit. Since it's a binary format and we just care about the data, we're just emitting that, and remaining, the viewer will take up that and fill up all this information so that like it's around like 20 cycles you can get this kind of a trace. If you want to do this with printf kind of a thing, it's like around, much bigger than that, something like 400, 500 cycles. Yeah, so this is like a quick overview of like the previous command, how we can see as in a trace viewer. Yeah, so next one is a graphical based trace viewer. It's called Trace Compass. It's also free. It's open source one. You can just download it. So it has a similar information. So I just fed the same file to the Trace Compass. So you can see, you can see the timestamp, and it's going to say which CPU and the event type and the content of that. And the beautiful part about this tool is like there's a histogram, right? So we can see like when these events are generated, and there are means in this tool, like if you select this to this, then you can see what's the time between, the delta between this time. And it also has a lot of plugins where like it can analyze looking at this pattern. Like for example, like you can write a custom script to see like, is there any memory leak? Because if you count the alloc and free, if it's not adding up, then it's going to be a memory leak, right? So all that post-analysis tools are possible by even this has a framework for that, or there are Python modules who understand the CTF file format, and we can write our own, right? So when it get into the post-analysis, then there are infinite options are available to tune the post-analysis, which is specific to DPDK, because we are emitting all these trace points, and based on this data, we can come up with a lot of things like, right? So that's the thing. Now, this is all in terms of the usage, and you can also add the bookmarks in this tool so that you can see, later you can poke around that trace. This is like short summary of the trace viewers. Now let's get into the details where how we implemented it. So the first thing, like we need to know the CTF file format. It's a bit complicated. It's meaning high level specifications, but I will just summarize what like high level view. The spec is there. It's here. And so if you see the trace CTF trace structure, they called as in streams. And there is a metadata stream. So for DPDK, I map this as each stream is one thread. And so if you see the amount of files generated when you give an RT underscore trace underscore save, is like if the system has n number of threads, n plus 1 files will be created. So each, the plus 1 is for the metadata stream, but n files for each thread, which is going to have an array of events, trace events associated with that. And now let's get into the peek into the metadata stream, right? So I've decided to have a metadata very minimal, so that we can get a high performance. There is a minimum amount of overhead to generate the trace file, because we are able to do that, meaning in FastPath we are getting around 16, 17 cycles to emit a trace point, right? So we cannot add a lot of overhead. So the metadata is based on SweetTF specification 1.8. So there's two parts, right? So the implementation is going to create this file at runtime. So this file will be read by the viewers to understand the event layout and how the events are embedded in a file, right? As an implementation, we will be creating this file runtime based on the events we registered. And the viewers will take this file along with the streams, which is like trace buffers for each core. And using this metadata, viewers can understand what is the content of the file and start decoding that. So let's see a view of like how the meta file looked like. So this is, I took a snapshot of this from current generated CTF metadata from a current implementation. So the first section is, it's like defining the data types, right? So the spec is not aware of uint64 and all that thing. So you just, first section is like defining the data, meaning how the data types looks like, and how the string type look like, and how the floating look like, and how the double data type look like. This is quite generic. I think all the meta files will have this thing because it's a common thing. So we pull that in. And next thing is like kind of start specific to DPDK. So the next section is called trace. It's going to tell like major and minor number and UID. So it's quite common. And byte order, it's in linked linear. Now, so if you see that trace buffer, so a single core, similar amount of, this is the buffer layout it's going to be created. So we have a packet header. So that's going to decide by this metadata. So in the packet header is going to say like, you have a 32-bit magic number and you have 16 bytes of UID values. So it's quite common in all the header, but we can add a new information if you want, but DPDK, I don't see any other information is required as a top level context. And yeah, then there is a environment variable section, so you can give the couple of key and value pairs, what you like to have. So just given the DPDK versions and trace name as DPDK. Now the clock. Okay, so this the clock is actually it's derived based on RTDAC. Okay, so the system I was using, it was running at 2.6 gigahertz. So that's why this created. And yeah, so there is specific routine to figure out like, this steps talk about like when the trace points are started, right? So if you see the trace viewers, it's giving a value in the absolute time, right? So this is just telling like since the epoch 1970, what's the seconds happened, so that you can get the time in current time of the day, right? So we will be populating this number by reading the clock in DPDK and figuring out this value based on the epoch, meaning 1970. Since 1970, how many seconds are elapsed? All these things will be runtime created. So this is a clock section. And this is going to say like, what's the clock granularity? I choose to have a 48-bit value. So I'll decide why it is that. And the packet context, okay, the next one is the stream context, yeah. So in the stream context, it's going to tell the packet context. So it's going to tell the CPU ID and the thread name associated with that. And each event, so this is going to define each event header. So, okay. I choose to have to get a high performance, just a 64-bit header, which has 48-bit represents the clock, the timestamp, and 16-bit represents the ID. The ID means the event ID. So if you see that, so this is like the header, then followed by, so if you see the metadata file, there will be a lot of sections called event, and each event will saying an ID and name of the trace point and the fields. This is a syntax used by the CTF. So if you see, remember the first example where we are just registering a app string, right? So it will be just translated to this kind of a string so that viewers can understand. So yeah, so eventually this file will have all the events and it will have an ID, okay? So yeah, so the viewers typically, so once we give this patterns, then viewers can start understanding what the layout look like, right? And start parsing the buffers and start displaying it in the form it wants, right? And so finally, I just want to give a high-level notes on how the trace buffer memory layout is, which is basically based on this layout, which is exclusively created for DPDK to have a very less overhead. So which translate to like, so yeah, first like there will be like n number of trace buffers per thread so that there is no locking requirements. And if you peek into each threads, like you will have a memory like this. It's like, which is controlled by a trace buffer size. By default is 1 MB. So it starts with a packet header, which will have a magic and UID value, which is what metadata defines, and thread ID and thread name. So it's a packet context. So these 4 parameters will be created in slow path, which is the header for the file. Now actual data path real action comes. So when you emit a trace point, it's going to write a 64-bit, which consists of event ID of 16-bit and timestamp of this thing, right? So the beauty is like how quickly you can form this 64-bit keyword and write to this memory, right? And also considering a different mode, right? If you give it as a overwrite mode, then it's a circular buffer. You need to go back, right? So all these things is happening in 17 cycles or so if we decide to do that. So this is a event 0 trace header followed by the payload. If it's like a U in 64, like an 8-byte data will come there as a little endian. And followed by, if he has a 32-bit data, then there is another 32-bit data will come, right? So that's just a payload, right? It's just a compact binary format, and just care about what is the content and what is the meaning of content will be defined in the spec file, right? The meaning in the metadata file where you don't need to emit those in fast path, right? That makes it very extremely fast when you deal with the trace thing. So likewise, like, so when we emit a next event, another header will be generated based on the timestamp and event ID, and the payload will be generated. Likewise, like once it's overflowed based on the mode, if it is discarded, it will not be writing anything more. If it is an overflow, meaning overwrite mode, then we'll come back here and start writing it from there. Yeah, that's pretty much I have for the tracing. Open for
Jerin, we have a question from live chat from Roger Melton. Asks, also, is the DPDK tracing implementation 32/64-bit clean? Or more specifically, has it been tested with 32-bit app?
Yeah, it's 32-bit clean, but I'm not specifically tested for 32-bit.
Do we have any other questions for Jerin?
I have another question, or that's more a kind of a comment. So we used the CTF format internally as well, and there's this great bubble trace tool you showed. And you can even write custom plugins right easily for this bubble trace tool to extract the information of the trace you need there. But I tried to integrate the DPDK tracing into my application as well, and I basically totally failed. And that was because I didn't understand the API. So we should really try to improve the API around the tracing library, especially about the semantics. So what do I have to do first? Like register a trace point? What arguments do I need to give to the macros? Because all that is not self-describing.
Actually, we have a user guide which has a trace point, meaning trace, it's an exclusive page for tracing, and we have all that information there. Have you looked into the documentation?
So I looked into the API spec, and this
No,
is
not
quite
API spec,
sparse.
the user guide.
Okay, then I will have a look there.
Yeah,
as
the
well.
programming guide talks about all this information like internal details and how to add a trace points and stuff.
Okay, thanks.
So another question about enabling and disabling the traces. Is it done via some sort of flipping of a global flag, or are you rewriting the code, basically insert a NOPS in a place and then rewrite that to a call to a function?
No, it's just, it's a circular buffer, we are maintaining head and tail pointers.
Oh no, sorry, a different thing. So at runtime, I can enable tracing a particular trace point, right? Or disable it.
Okay,
So
yeah.
that bit.
Yeah, that's based on an if check, basically.
Oh, okay.
That brings, so the DPDK, we cannot change the instructions at runtime because like kernel, you are mapping the instruction and you can play with it, right? But here, like Linux loader is giving that thing, right? So you need to mmap, and it's so much of complexity to change the instruction stream at runtime.
Does the memory, the trace buffer is it backed by a huge page by default? That's what you said,
default
right?
meaning if you give a huge page, if you don't give huge, then it's
Okay.
based on.
So if you have like a secondary DPDK process, you could read that page. Am I correct?
Yeah, we
Okay,
can.
so that would be a cool technique if somebody wants to have like a continuous trace that is larger than, let's say, 1 meg. You could have a secondary process that could continuously read from that buffer. You could have like infinite stream of traces, basically recovering by timestamp, right?
Yeah.
So yeah, that's cool. Thanks.
There's actually another part of the question from Roger. He had said, does tracing itself work if symbols have been stripped from the application?
Sorry, tracing?
Does tracing itself work if symbols have been stripped from the application?
Yeah, it'll work because we are exposing the trace symbols into the map file. Yeah, it is going to work.
Any other questions for Jerin before we wrap up? No? Okay, thank you so much, Jerin. Appreciate your time.